9 minutes. One battery. 70 degrees Celsius. The internet called it dangerous. Battery experts called it reckless. An entire industry said this was beyond the safe limit, that BYD was quietly cooking its own cells in the name of speed. BYD's top scientist had one response. He called it the future. A Chinese blogger plugged a BYD into one of the company's new 500 kilowatt flash chargers. The result looked like something out of a tech demo. 10%to 70% in under 10 minutes. Numbers that would have been dismissed as fantasy just 3 years ago. But then came the screenshot. Battery cell temperature, 70 degrees Celsius. That single data point detonated a firestorm online, particularly across Chinese tech forums and EV communities. The accusations came fast. BYD is cooking its own batteries. Flash charging is quietly destroying long-term capacity. The heat is too much, and at the center of it all sits a very real, very legitimate engineering question. One that even serious battery researchers have asked. Here's the concern. Lithium iron phosphate cells, the chemistry BYD uses in its Blade battery, have traditionally been considered safe up to around 60 degrees Celsius under load. Push beyond that threshold repeatedly, and you risk damaging the SEI film, the solid electrolyte interface. Think of the SEI as the battery's internal armor. It forms naturally on the surface of the anode during the first few charge cycles and acts as a gatekeeper, controlling which ions can pass through and which reactions are allowed to happen. Degrade that layer and the battery loses capacity permanently. So the question isn't just internet outrage. It's grounded in real electrochemistry, and it deserved a real answer. Sun Huajun, chief technology officer of BYD's battery division, stepped into the controversy at the Beijing Auto Show. He didn't deflect. He didn't offer corporate non-answers. He went straight at the criticism. His core argument: 70 degrees Celsius is what he called a cognitive boundary of the past. Not a physical limit, not a chemical limit, a psychological one, inherited from an earlier era of battery design. To understand what he means, look at the history. When fast charging first moved from 1C to 2C, roughly from 50 kilowatts to 100 kilowatts, the industry warned about heat damage. When it jumped again to 5C, pushing toward 250 and 300 kilowatts, the same warnings appeared. And every single time, new materials science arrived and rewrote the rule book. The goalposts moved because the engineering moved. Sun's point is that 60 degrees was never an absolute physical ceiling. It was the safe operating limit for the battery designs of that generation. Designs that didn't have the thermal architecture to handle more. So the industry drew a line, and that line calcified into conventional wisdom. BYD's second-generation Blade battery was engineered from the ground up to operate differently. The cell uses a symmetrical internal structure with dual-surface cooling, meaning heat is extracted from both faces of every cell simultaneously, not just from one side as in conventional designs. BYD also refined the cell's physical dimensions to minimize internal resistance, which is where most of the heat originates in the first place. Lower resistance means less energy wasted as heat during high-current charging events. The result is a pack where temperature rise is not only faster, it's also more uniform and more controllable. 70 degrees becomes manageable, not because BYD is ignoring the heat, but because their thermal management system was designed specifically to handle it. This is the distinction that gets lost in the online debate. The question isn't whether 70 degrees is hot. It clearly is. The question is whether the system surrounding those cells was built to operate safely at that temperature. And according to BYD's own validation data, it was. Claims are cheap. Data is harder to argue with. Before a single car equipped with this battery left the factory, BYD's engineering team ran over 1,000 full flash charge cycles in controlled validation testing. For context, most consumers will never perform 1,000 full charge cycles across the entire lifespan of their vehicle. The average EV driver charges to full perhaps 2 or 3 times a week. At that rate, 0 full cycles represents roughly 6 to 10 years of real-world ownership. BYD didn't stop there. They also ran simulated long-distance endurance scenarios, the electrochemical equivalent of driving from China's southernmost tropical coast all the way north into the sub-zero temperatures of Manchuria, repeatedly, under conditions that stress both the cells and the thermal management system simultaneously. These aren't static lab tests. They're dynamic load profiles designed to replicate the worst conditions an owner might encounter over years of use. Even at minus 30 degrees Celsius, conditions that cause most lithium-based batteries to charge at a fraction of their rated speed. BYD's second-generation Blade battery completes the same 10% to 70% charge in just 12 minutes. 3 minutes slower than at room temperature. That's not just impressive. That's a fundamentally different level of low-temperature electrochemistry. Sun acknowledged that independent long-term data from real-world owners will be the ultimate proof, but he made a pointed observation. 1,000 full flash charge validation cycles is more stress testing than most fast-charging systems in the industry have ever undergone before deployment. Sun didn't stop at defending BYD's own technology. He used the moment to draw a sharp contrast with CATL, the world's largest battery manufacturer and BYD's most formidable rival. CATL had recently suggested that equipping vehicles priced above $36 with lithium iron phosphate batteries represents a step down, a compromise on performance. The implicit argument: high-end vehicles deserve nickel manganese cobalt chemistry, the denser, more energy-rich cells that CATL supplies to premium brands. Sun's response was direct. He pointed to the Yongwang U9, BYD's million-dollar hypercar, which uses LFP-based chemistry and still delivers supercar-level acceleration, lateral dynamics, and driving precision. His challenge: who actually gets to define what high-end means? A cell supplier drawing distinctions based on energy density metrics, or the driver who cares about charging speed, system longevity, safety under stress, and predictable real-world behavior? His answer was unambiguous. Safety is the ultimate luxury. And on that dimension, lithium iron phosphate wins by design. LFP chemistry does not undergo the same thermal runaway cascade that makes NMC cells dangerous under mechanical damage or extreme overcharge conditions. It is inherently more stable, not because of clever engineering around it, but because of its fundamental molecular structure. Sun did acknowledge LFP's current limitation. Energy density at the pack level sits around 130 to 140 watt-hours per kilogram. That gap remains real. CATL's own LFP cells have pushed higher, and Gotion, backed by Volkswagen, recently unveiled a sodium-based cell architecture reaching 261 watt-hours per kilogram at the cell level. BYD is not standing still. The company is actively developing sodium-ion, solid-state, and lithium-free anode technologies, each aimed at closing the energy density gap without sacrificing the thermal safety profile that defines the Blade battery's identity. BYD is currently building 20,000 flash charging stations, each capable of delivering 1,500 kilowatts across China, with expansion underway in Australia and Europe. By early May, 6,000 stations were already operational. That deployment pace outstrips the entire fast-charging build-out that most Western countries have managed for their national networks. The speed of that rollout is partly possible because BYD backs each station with large stationary battery buffers, decoupling the charger's peak output from the constraints of local grid capacity. It's a systems-level solution to an infrastructure problem that has stalled competitors. Sun's final point deserves to stand on its own. Anyone can build a 1C or 2C charger, getting a reliable, safe, 9-minute full charge. One that doesn't quietly degrade the battery over hundreds of cycles, requires a depth of electrochemical research, systems integration, and thermal engineering that most organizations simply haven't invested in yet. The debate about 70 degrees will continue until independent long-term owner data arrives. That data will take years to accumulate. But right now, BYD holds a lead in this race that no competitor has come close to matching. 9 minutes. The clock is running.